Introduction to Hydrocarbons Lab. A couple of safety notes. Make sure that you keep the tops or caps on all the containers because organic chemicals are quite volatile. The fumes are unhealthy and they're flammable, and turn on the fume hoods while you're using them. Use goggles and gloves. The first part of the lab is information and the shadow structures, and some of the structures are some things you can do during lab time if you're waiting for a area to be vacated, or if you have some time when you're finished. One of the neat things to look at is to look at the shadows that you get by using the overhead document camera, and these are some pictures that I've taken. If I simply sit a methane molecule and I've got black for the carbon and I'm representing the hydrogens with yellows here. If I simply sit that on the 3 carbons and look down on it, what I see are 3 positions. But what you typically see in textbooks is that carbon is written like this. And part of the reason for that is if you allow that carbon, that methane, to sit on 2 of the hydrogens rather than all 4 of them, you would actually get a shadow that looks like the structures that you see written in books, the 2-dimensional structures. Whereas when we try to draw carbon as a 3-dimensional tetrahedron, we would draw it this way with the carbons and the hydrogens out here. Some other things that you can investigate with models are the fact that single bonds you can rotate around. So if this is a single bond, this bond can rotate. And particularly if I have a substituent on it or 2 substituents, you can see that there are better ways for that to fit and not so good ways. So even though it rotates, it may spend more time in one particular position than another. But what I've done here on ACD Labs is gone to the 3D viewer and rotated this around a little bit. So this particular structure is looking straight down this axis. And you can see that this is what we call a staggered conformation. On the next slide, I've got a staggered conformation here, but here's an ellipse conformation. And so with hydrogens, that's not too bad because hydrogens are pretty small. But if I had a bromine attached to each one of these carbons and had that in the ellipse conformation, in this space-filling model, you can see that the bromines, their electron clouds interact, and that would not be something, that would be a very high energy state for that. So these would be much better if these bromines are much further away from each other, and they probably rarely, if ever, look like this. Even though it's possible, they can rotate around to do that. So that's something when you build some models you can practice. And part of the rest of the assignment here is just to draw some models and then actually to draw some isomers where you have ethane and you put 2 bromines on them. What possibilities do you have for isomers, and what would be the names? And ethylene, where you actually have a double bond, how can you draw those, and what would be the names for those isomers? And then cyclopentane. With both ethylene and cyclopentane, you have either a double bond or a ring, which constrains the ability to rotate. So you're stuck with a certain position. So the rest of the lab talks about some of the actual activities you can do with the chemicals. So in the first hood in the front of the room, we'll be looking at properties of hydrocarbons, and we have hexane, 1-hexene, toluene, and lamp oil. So we have saturated, unsaturated, and aromatic hydrocarbons. For this, make sure you're wearing gloves. Make sure you keep the caps on. There are droppers which probably work better than the droppers that are in the bottles. but make sure you keep a particular dropper with its bottle. Don't get them mixed up. There's distilled water over here because the first one you're looking for are any of these soluble in water. So put in a few drops of the hydrocarbon, put in a few drops of water, mix them up a bit, and look to see whether you can see mixing or separation. When you're finished with that, you can pour the waste into the waste container. But you will do 2 other experiments with this. The next experiment is to look at combustion, and you can use each one of these, but you're going to look at the difference in sort of in the amount of saturation and what it does to the color of the flame. Complete combustion gives you carbon dioxide and water. Incomplete combustion will give you carbon or a lot of soot. So there are wood splints and matches here. You'll put a few drops of the hydrocarbon on a watch glass, and really you are igniting the fumes. So don't think that you need to stick your lit splint into the liquid. You want it just above the liquid. It's the fumes that ignite. But you really want to investigate the amount of smoke you get and the amount of residue and the color of the flame. And you can write an equation for hexane, hexene, and toluene. Lamp oil represents kerosene, and it also is a mixture. And then a test for unsaturation, you will be using the bromine in dichloromethane, and you will see if bromine can add across or open that double bond. If it does, the highly red colored bromine, when added to your solution, will turn clear or just a pale yellow. And if that happens, you've got a reaction. If you drop it in and nothing happens, there's no reaction. If you do get a reaction, you might want to try to add more drops and see if you get to the point where you have completely reacted all the double bond present, but don't add any more than 20 drops. Make absolutely sure that you recap these containers and keep the droppers with the right solutions. When you're finished with these, you can again pour the waste into the waste container. You may need to ask for a few more test tubes here. I think I don't have enough out. The original solutions are sitting back here. You shouldn't need to use those, but they are there. In the second hood, you can investigate the properties of cis and trans isomers. We have fumaric acid and maleic acid, which are both diacids. So the difference in structure is the double bond, and are they across the double bond or on the same side of the double bond. One of the things to investigate is melting point, and you need to put a similar pea-size piece in each of 2 small test tubes. Using the test tube holders, heat them both at the same time, and just look for which one melts first. We're not asking you for a temperature, we're just asking you for which one has the lower melting point. After they cool, add a few drops of water and see about their solubility. Polar compounds should be more soluble, and actually the polar compound should have higher melting points, but I think in this case there's a lot of what we call steric hindrance and perhaps has a lower melting point. Now, in going back to looking at polarity, here are some compounds which you can determine whether they're polar or not. One of the ways that I do this is to add, these are carbons here, to each of the elements, and then look at the way the arrows point. The arrows will be pulled towards the higher electronegative element, and in this compound you can see that basically this is polar. The oxygen is pulling electrons toward it. But you can do this in several other of the compounds. For example, in these substituted aromatic dichlorides, it is mainly the position of the chlorines which tells you the polarity. So in investigating polarity and solubility, a basic premise is like dissolves like. Polar things tend to dissolve other polar things, and nonpolar, nonpolar. So what I'd actually like you to do is go through this and tell what you expect, yes or no, if they're soluble, and then go back and actually look, because I've got samples back here, and you should be able to tell whether you see solubility or not. And lastly is another investigation on polarity, and this is column chromatography, separating the two colors that make up the coloring for grape soda, the purple color for grape soda. You'll get a pink and a blue. We have water, grape soda, and then two concentrations of ethanol, 95%, which is the more nonpolar of the two, and 10%, which is the more polar of the two solutions. A couple of things to be aware of. You will be using 24 well plates instead of test tubes to collect anything from the column. The columns can be reused, so when you're finished, make sure you go through the rinsing process for the column and leave it here. The columns fit onto the syringes, and you put the short end of the column onto the syringe, and I have syringes hooked up so you can see how they should look. Additionally, you will only push fluid out the column. You will not pull fluid back through the column. So when it asks you to fill a syringe with grape soda, for example, take the column off, fill the syringe, and then put the column back on and push it through the syringe. So I have the directions there, and hopefully you can follow that. When you're finished, you can dump the materials from your well plates into the waste container back here. So I hope you enjoy and learn something from these labs. If you have any questions, ask the instructors, and they can also call me if necessary.